Oof. Good evening. Can everyone hear me okay? You guys can hear me all right and back? Good? Okay. All right. Thank you all very much for coming this evening to tonight's forum on the science, technology, and economics of climate change. There's a few organizations I want to thank in particular for making this happen. It was organized by the student group Students for Iowa PIRG, which is a group that runs campaigns in the public and student interests. And the current campaign that we're running is called the Campus Climate Challenge, and it seeks to promote awareness and formal education on climate change and energy issues, and to push for policy reform at the local level. Also, I would like to thank the Committee on Lectures for co-sponsoring the event this evening. And, of course, I would like to thank the government of the student body because they fund both organizations. This evening, tonight's event is being run in part with over 1,500 institutions across the country under the banner of an organization called Focus the Nation. They've been organizing a national climate change teach-in for a couple of years now. In order to help make this program a success, I'd encourage you all to sign in. And if you haven't already, then just make sure you catch one of the youngsters with clipboards running around before you leave this evening. And it'll be very much appreciated. Tonight, we're here because humanity is at a crossroads. Tomorrow's actions will have huge natural, economic, and political impacts for decades to come. And as this issue has escalated, not just at the national level here, as we've seen the last year or two, but internationally, it's come to our attention that a more deep understanding and thorough commitment from our not just our politicians, but the media and our public as well, is due. Unfortunately, our federal government has shown a lot of reluctance to even let the science speak at the federal level. And we are, however, in a fortunate situation to have a federalist system where the lower levels of government can express their leadership. And in fact, this form of leadership has taken the form of state actions, local actions, and even institutional actions to make climate change a more pertinent issue and to begin to reduce our impact. Speaking of institutional action, just last week, the president of Iowa State University, Dr. Joffrey, announced his President's Advisory Committee on Energy Conservation and Global Climate Change. That's a mouthful. But this is an outstanding landmark step for this university. And in his commitment, he's outlined 4 goals. One is to conduct a full-scale university energy audit, and he plans to ensure that this energy audit is used to develop plans to both reduce our energy and reduce our carbon footprint here at Iowa State. And lastly, he wants to ensure that students and the ISU community are well informed on alternative energy issues, energy conservation, and the science behind global climate change. And this last goal is a big factor of what we'll be doing here this evening, and this is hopefully an event that we can continue on an annual basis. Tonight, we are lucky enough to have 3 distinguished faculty members at Iowa State. The first up will be Dr. Eugene Tockley. He is a professor here in the Geological and Atmospheric Sciences Department, and he's also a contributor to the UN Intergovernmental Panel on Climate Change, which is the group that won the Nobel Peace Prize just last year. Following him will be Dr. John Miranowski, who is a professor of agricultural economics and is the director of the Institute for Science and Society here at Iowa State. And finally, discussing the solutions will be Dr. Vikram Dalal of the Electrical Engineering Department, and some of his current research focuses are on increasing the efficiency of solar cells. And the format for tonight's evening, each of our panelists will speak for 20 minutes, accompanied with a PowerPoint presentation, and at about 8 o'clock, we will open it up to questions and answer session from all of you, and we'll do that until 8:30. So hopefully everybody that has a question will be able to get it answered this evening. So I would like, please give a warm welcome to our first panelist, Dr. Eugene Tockley.
Thank you, Devin, for that introduction, and thank you for your leadership and on these issues on the campus. For those of you who don't know Devin, he's an honors student and in political science and has been very active in this before it became fashionable. So we thank you for your leadership on that. This is a nice photograph. Let's see, is it possible to douse the spotlights here? Maybe not. Maybe it'll be all right. This is a NASA photograph that I really like. That it's actually a composite of several photographs, but it shows that the planet Earth is a green planet, it's a blue planet, and it's a white planet. It's a blue planet because it looks blue because of the refraction of water. We have water in liquid form on this planet. We have white, which is in some places clouds, and in some places up here it's ice. So we have water in vapor form. So we have water in all three phases in large abundance on this planet. It's also a green planet because there's life on the planet. So it's the only place we know of in the universe where we have this special range of temperature and the special protection from the lethal rays of ultraviolet light that come from the sun that protect this environment we live in and make it hospitable to humans and life as we know it. And that we are protected from this exterior environment by this thin shell of atmosphere, which is, if the Earth were the size of a basketball, this atmosphere would be the thickness of about 2 sheets of paper. And there are 2 gases in that atmosphere that protect us, and those are ozone, which protects us from the lethal rays of ultraviolet light, and the second is carbon dioxide, that keeps the balance of temperature within a range that life can exist as we know it. And so now we know that carbon dioxide is on the increase, and so there's a question of what is going to happen from here. And so I've raised the question, 2 questions here. How did we get here? I'm going to talk about that a little bit. That's the science, and our follow-on speakers will add more detail to this second question, what do we do now? So let's see. Get it right here. This shows 3 graphs. I'll just focus on the first and the last. The first one is a plot of carbon dioxide over the last 400,000 years, the present being over here on the right, the past being here 400,000 years ago. You can see that carbon dioxide has gone through patterns, cycles of high and low amounts ranging from about 180 units here, it's called parts per million, up to about 300, and there have been natural cycles, and we know the reason for those relating to the orbit of the Earth around the sun and a wobble on its axis and so on. You can see that temperature tends to follow a similar kind of cycle. Oh, thank you. And these are natural cycles, and we can understand and explain those. But now recently we have had a very large increase in carbon dioxide, adding on the order of over 7 gigatons of carbon dioxide per year to the Earth's atmosphere. For each of us here in the state of Iowa, probably with our use of energy and all the stuff we buy and so on, we each probably account for about 20 tons of carbon dioxide. So if you want to think about cleaning up after yourself, you have to think, how much would it take? How would I get rid of my 20 tons this year? Because it's going to be here. If I don't clean it up, 7 of those tons are going to be here at 2,100, and probably 2 of those tons are going to be here in 2,200, all the time contributing to an imbalance in the energy and to the process of global warming. So right now then, we're at 385 parts per million, so we're off the chart here, and we're headed with business as usual to probably 4 times the pre-industrial level by the end of the present century. So the question is, what's going to happen to this red curve? And what's going to happen to the ecosystems on our planet? And you can see that it's not only the magnitude, but it's the rate of change that is important here. That in the past we've seen changes, but there have been a few where it's been relatively abrupt, but many of these changes have taken place over centuries or several dozens of centuries. And what we're seeing now is something that's really not a part of the natural system. So, well, I don't know. Let's see. What should we do with that? I guess I can't remember what that was. But anyway, this is a picture of the ice, sea ice on the North Pole. The North Pole is here, and you can see this dotted line is the outline of ice in the summer. It's the summer minimum, and the average over the period of 1979 to 2005 is shown here in this with this orange line. And so if you watch that line, now this was from 2003. Let me just cycle this forward. There's 04, 05, 06, and there's 07. So we've had a dramatic loss of ice in this past year. Now, we have to look at this a little bit objectively. There is some evidence that the wind has blown more directly from this direction in this direction. So there has been more wind this past year blowing ice toward the pole, actually, and which contributed to this large loss here. But the fact that the ice has thinned has allowed this to happen. So this rate of ice loss is far greater than was predicted by climate models. On Greenland, we have regions shown here in pink that where melting occurs on a seasonal basis. Every summer, this region in pink in 1992 would melt. In 2002, now that melt area has increased dramatically, and you can see here's a line showing the increase in melt area. So we're seeing much more water on huge ponds and lakes on the ice surface, and so you see something like this. And these large lakes will eventually find a crack. And when they find a crack, a little crack, they make it a big crack. And a big crack leads to water cascading all the way down to the mountain surface, which then leads to movement of ice down the mountainside. And these chunks of ice, some of them are large enough, they're the size of Manhattan and the height of the Empire State Building. So when they start lurching down the mountainside, they set off earthquakes. And so we can measure the number of earthquakes. The number of earthquakes has tripled in the last 15 years on Greenland. So, and it's in the summertime that they're increasing. It isn't year-round. So, and it's not just a general increase in earthquakes, but it's related to summertime melt. This is one. Could I put my computer up? Sure. We're missing some key. Just leave it. I'm missing my pigtail.
Sorry about
Does this
that.
have a? Does this have a? The other? No, it doesn't. Okay, well.
You need the adapter folder.
These slides here showed a confirming evidence that we know the reason for the recent warming and why the recent warming is different from warming of the of the earlier part of the present century. One of the hey, terrific. But this doesn't have the. No, this doesn't have the other thing. I need the other. Sorry. Other Mac users. This plot showed that there is an increase in there was an increase in temperature from about 1910 to 1940, and another increase in temperature, global average temperature, from about 1960 to the present. And they look about the same, these two periods of temperature increase, global average temperature. The question is, what caused those? And it's just been recently that we've been able to clearly attribute the first of those two intervals to fluctuations in the output of the sun, whereas during the second of those, it's been primarily due to greenhouse gas warming. And so there's been some very good criticism leveled at climate modelers saying we've seen increases in temperature in the past that are similar to what we're seeing today, and if you can't explain those, then you can't attribute the current rise in temperature to greenhouse gases. This curve, produced by Jerry Meal at the National Center for Atmospheric Research, pretty well confirmed that that was attributed these. Oh, here's a follow-on figure that shows the results, the consequences of this. Here you can see this is a simulation of temperature over the last 110 years or so. The black line is the observed global average temperature. The blue line is if we were to rerun that climate model but not put in the effects of greenhouse gases or sulfate aerosols. In other words, this is what the planetary temperature would have looked like had we not put either greenhouse gases or sulfate aerosols into the atmosphere, and so it would have looked like this. When we put in the effect of greenhouse gases and aerosols, we get the red curve. And you can see that the only way you can explain the current rise in temperature is by putting in the anthropogenic contributions. So we have very clear evidence that the current warming is due to the combination of greenhouse gases and sulfate aerosols. If we look to the future and we choose some kind of energy use scenario, anywhere from energy intensive to reduced consumption or maybe even strong energy conserving, or constant composition, that is, the constant composition is that we don't emit any more greenhouse gases starting right now. Turn off the lights, no more greenhouse gases. Then we would get this orange curve. So we go from this red to this is extreme energy intensive to using no more emitting no more greenhouse gases. You can see that in any case we're already committed to a warming, even if we take a very energy conserving scenario. And if we put we notice that we are already committed to a warming of 1.5 degrees or so, and so we really need to think about the future in terms of two parts. We need to think about a mitigation phase, which is the latter half of the 21st century, which is our target period, that we need to do something so that we don't have this kind of warming. But in the first part, for the next 50 years, we're already committed to a warming. And so the key there should be adaptation. What's going to change, and how should we adapt to that change? I mean, we also need to mitigate for the short term, but we have to recognize that even if we take heroic measures in the short term, we will not feel that for about 50 years. If we look at what the future holds in terms of the end of the century, red and dark colors here indicate warming. You can see that the polar regions are going to continue to warm substantially. If we look at precipitation, the polar regions and the high latitudes are going to get more precipitation than low latitudes. And in fact, it's the subtropical high pressure zones. Many of these are regions of poor and food-strapped economies already, and we're projecting that the growing conditions may even be worse in some of these countries. So Devin has already talked about this committee, so I'm not going to talk about that. Where do we go from here? Well, I'm going to talk just about Iowa State's research role. Others will talk about other aspects, but there's four things that we're doing here. First is that we're a part of the North American Regional Climate Change Assessment Program, and what we're doing there is we're trying to produce information that can help us understand what's going to happen locally. If we just take the results of global models, this is what we get. This is what the North America looks like in a global model. So let's suppose that you're doing a study on the Central Valley of California. Well, Central Valley doesn't even show up. There's a big bump here out in the Great Basin, so the mountains are even in the wrong place. And poor you if you're in Florida trying to study citrus. You see, Florida doesn't even exist in this global model. So what we're doing is using regional models embedded in global models, and so that gives a picture of the U.S. that looks like this. So we'll be providing climate change information at higher resolution than is available from the current range of global models. Second is a program called MICA, which we have proposed, which gets at the issue of seasonal forecasts and how we might be better able to adapt to seasonal fluctuations in climate. Some will argue that we're seeing more fluctuations, more extremes of climate now than we have just 25 years ago. And that's certainly true for precipitation. We have more precipitation now than we did 25 years ago. We have much higher winter temperatures than we did 25 years ago. Oddly enough, in the center of the country, we have lower daytime maximum temperatures in the summer. Also, probably linked to global warming in a counterintuitive way. We're seeing more extreme events in precipitation. So and these are all consistent with climate change. So the question is, how can we make sure that our agriculture and that our use of water and so on, our human health, is robust to more extremes in climate if that should be our future? So we're using this. We're going to do seasonal forecasting with an ensemble of climate models, and we'll be looking at addressing questions like this. How will new trends and variability of regional climate affect any of these and a lot of other issues? Building designs, human health. If we're going to change our agricultural tile drainage systems, for instance, how should they be structured? You put a tile drainage system in, you expect it to function for 50 to 75 years. So what's the precipitation regime going to look like in 75 years? Well, it would be good if we used at least our best estimate of what that situation would be before we put that tile drainage system in. So the question is, who's going to provide this kind of authoritative information? Right now it doesn't exist. And then secondly, how will it be delivered? And that's so what we're doing here is working with our scientists across the campus and also with our extension service. And so we're going to be working with a consortium in the Midwest, 9-state region, and the agricultural extension services in those regions. The next one is actually it's very similar to the previous one, using an ensemble of models. That is, rather than use a single model, we'll use a variety of different models to get a better estimate of what our seasonal climate is going to be. And finally, Vice President Brighton has launched a climate science initiative. Colleges of Agriculture, Engineering, and LAS are taking leadership on this, but we expect that there will be broad participation across the campus to build on the strengths that we have in agriculture, in climate modeling, and landscapes, engineering, social sciences, which are going to be an important part of this, economics, to try to address this issue from a very broad perspective, to better enable us to do what we need to do to adapt to climate change. Thank you.
It's a great pleasure to be here talking about this topic tonight. It's also a challenging one because more of what we don't know than what we know when it comes to climate change, and what we have not discovered yet about how effectively different policy choices and policy options are going to work. Before I start with my comments, though, I'd like to ask you a couple questions. One is, how many people in the room think that we have greenhouse gases accumulating in the atmosphere too rapidly? How many people in the room would be willing to pay something to reduce the greenhouse gas accumulation in the environment? How many people in the room would be willing to pay a lot to make sure we have some reduction in greenhouse gas emissions, or a significant reduction? Okay, you've stole one of my points here, but I'll come back to that. One of the problems that we have when we're looking at greenhouse gas emissions is that we're dealing in a global environment. And what I want to do is start off with first talking about the evolution of air pollution policy in the United States, because our set of options that we're talking about really grew out of this. We started out early on with a command and control approach, both with water quality problems and air quality problems. And the government came along, provided direct regulation, provided technology standards that had to be used in power plants, in water quality plants and other production plants along the way. And to do that requires a lot of information. It's kind of treating everybody alike. So if one plant had to put an electrostatic scrubber on it, every power plant in the country had to put an electrostatic scrubber on it. And Senator Kennedy succeeded in protecting the Northeast to create a level playing field. So even if we didn't need it, if we were burning low sulfur coal, we put it on all the plants. And that type of an approach is not particularly efficient, because we're not getting the biggest bang for the buck or the most reduction in the process. In 1990, under the Clean Air Act amendments, we started playing with some other things. One of the things that we played with were voluntary programs. And some big polluters or big producers of emissions in the country have been allowed to have developed their own reduction programs, voluntarily reducing it by 30% or 50% their emissions. Now, one of the problems is we've never really studied carefully to figure out how effective this has been. It's good PR for the firm. They've made some investments, and it's kept EPA off their backs. And would that work in this particular case, dealing with greenhouse gas and carbon emissions? I don't think so. We've also talked about moral suasion. Be environmentally conscious, be green. I always think back, and this is really dating me, back to the energy crisis in the 1970s, when the White House of President Ford issued buttons that everybody wore around, "Don't be foolish." And it really didn't save a lot of fuel in the end. But there are a bunch of things that have been tried and done. And the other thing that's come out of the 1990 Clean Air Act amendments is a movement to what we would call more market-based solutions. Taxes or subsidies. And we go out and we subsidize certain things. We decide one way of reducing emissions would be to subsidize ethanol or biofuels. So we put a 51 cent a gallon subsidy on biofuels and ethanol, and $1 actually on biodiesel, to increase the amount of that material used, or that fuel used, relative to other fuels in the system. And so what we're doing is we're trying to move this process in a particular direction. Now, I would argue, if we didn't have a cheap energy or fossil fuels policy, we would have accomplished the same thing long ago. Because if fossil fuels had been a lot more expensive, it would have encouraged substitutes and the development of new substitutes and new technologies, including biofuels. The first example that I'm aware of burning ethanol in an automobile was Henry Ford's Model T. That was designed to run on ethanol, on blended ethanol, or gasoline, or some other, even I think kerosene for a while. And that technology actually was in use much more and produced during World War II when we were short of energy supplies. Ethanol production became a bigger thing in the scheme of things because we didn't have access to enough fossil fuels. So one of the things that's been used is subsidies. Others have been taxes. The Europeans, the South Americans, and so forth, all tax fuel at a much higher level than we do. And they drive, on average, smaller cars, more efficient cars, and so forth. And basically, the price is a driver. And that's why the market can work here. But we all know how popular more taxes are in this country. So that's probably not a very good option in terms of making this work. We hear a lot nowadays about cap and trade. And cap and trade basically is this. The government sets a level for emissions of carbon and emissions of greenhouse gases. And then establishes a market, gives permits to the people who are emitting these chemicals that allow them to emit so much. And then what they can do is the government establishes a market where they can trade these permits. And so if you can reduce your emissions more cheaply than the permit is worth, you sell your permits. And if you're inefficient and can't reduce your emissions very much, you buy the permits. So what we could do is cap the amount of carbon that could be emitted and then set up a market to accomplish this. Now, the Kyoto Protocol had some provisions for trading hot air from the Eastern European countries, whose economies had plummeted in the 1990s to about half the level of GDP that they had produced a few years earlier. And they were allowed to sell some hot air, if you will, to countries that couldn't reduce their emissions enough to meet the Kyoto Protocol levels. There was also trading with developing countries where the developed countries could buy pollution rights in developing countries as long as the developing countries maintained the Amazon forest or whatever it was, something that would sequester more carbon in the process. There's a Chicago Climate Exchange. It was actually established initially as part of the Clean Air Act amendments to deal with carbon. I mean, not with carbon, with sulfur. And that market has worked very well. But again, there are a couple unique features to it. It only applies to power plants, and generally I think it's mostly the larger power plants, have to get their sulfur level down to a certain level, and if they can do it cheaply, they sell their permits. If they can't, they buy more permits. And I think the price of sulfur is probably a little over $100 a ton. I'm not exactly sure, $100 to $150 a ton. The Europeans in the environmental trading scheme have, as part of the Kyoto Protocols, have set up the same kind of a thing in London. And that particular market has a price for carbon, the last I checked was about $25, $26 a ton. The U.S. Has the Chicago Climate Exchange, which also trades in carbon. What do you imagine that carbon would trade for in the U.S.? Oh, anywhere from $2 to $5, depending on when and where. Why? It really boils down to the fact we don't have a cap. So what's saving a ton of carbon worth? $1.50, $2. I mean, basically, the Iowa Farm Bureau Federation is a consolidator. They get farmers to participate for something like $1 an acre if they use no-till or reduced tillage practices and so forth. They consolidate these and trade them on the Chicago Exchange to get this market started, but they're not worth much, and so carbon sequestration in agriculture just isn't moving forward very rapidly in the process. A couple other things. Oh, the one other thing I want to say is, I'll talk about this in a few minutes, but this should be a global market. It doesn't make any sense for a particular country or group of countries to have a market when others can free ride and not participate, given that this is a global problem in its nature. There are also carbon standards and mandates, and these are kind of quasi-government regulations, market solutions. We see this now with the mandates and renewable fuel standards that have come out with respect to the 2002 Farm Bill and the recent 2007 Environmental Investment and Security Act. And basically the Environmental Investment and Security Act requires, I think it's 36 billion gallons of renewable fuels by 2020. And that's a mandate. Companies have to essentially build that in. There are some escape clauses on it, but have to build it in the process. Another thing that can be used are research incentives. And I'll let Professor Dalal talk about that to an extent in terms of some of the new solutions and so forth. But one of the things with research incentives is that we really don't have a very good arsenal of weapons at our disposal right now to reduce carbon usage. We don't have the best mitigations technologies. We don't have the best capture technologies. We can go on and on and on with some of the problems that are involved there. So we do need a better knowledge base and a better information base to make this work effectively. Even carbon sequestration in agriculture, we don't have a very good picture of what's happening in the process. Let me just spend a minute on this. This is something I use in my environmental economics class. If you look at this, and it's only to show you in a sense what policies will do, on the bottom of the graph, on the horizontal axis, I've got greenhouse gas reductions. And on the vertical axis, I've got the marginal benefits of these reductions and the marginal costs. And all I want to show you here is that the marginal benefits of more reductions are decreasing. The added benefits of more reductions in greenhouse gases are decreasing. And the marginal costs of getting greater reductions are increasing. And what we want from an economic point of view, if we include all the costs and benefits, is that we, at the intersection of those two graphs, is where we'd like to be to maximize social welfare. Now, the reason I wanted to show you this is that this explains in part why it doesn't matter what kind of a policy instrument we use as long as we let the market run that policy instrument in the process. If you set the cap at the level I've shown there, the vertical line, you can use a tax, a subsidy for reducing carbon emissions, or a permit in a cap and trade market, and you should end up with the same price. But you can also see the consequence if the government doesn't have the backbone to impose that restriction or that cap at a very restrictive level. If the government sets a cap back here, there's not going to be much supplied. There's going to be a big demand, and the market isn't going to equilibrate in any sense in terms of where we end up. So one of the things that happens here is when the government gets involved, there's got to be the political will to really change things. And that's very difficult to accomplish. Let me just touch a couple things on transboundary pollution and why this is a problem. This is kind of why we have inaction. By transboundary pollution, I mean pollution that doesn't respect political boundaries. And greenhouse gases are the notorious example of not respecting political boundaries. It's a global problem. The more we put up there, it affects everybody. But at the same time, why would you want to fix the problem here if nobody else is fixing it? Now, you can do that because you have a strong environmental commitment. You realize there's a catastrophe waiting for us down the road, not too distant, particularly for future generations. And so you get very concerned about this. But one of the problems that's associated with it is California, for instance, passed Assembly Bill 32 last year. And by 2009, they've got to have a program to reduce carbon emissions by 25 to 30% of the 1990 level in the process. And now they're trying to set this program up. Well, if they put the screws to the power companies, electrical power companies, what are they going to do? Well, the power companies will set up someplace in another state, and they'll import the electricity across from New Mexico or Arizona or someplace down in the south. Or if the U.S. adopted a program, or the European community, what would happen? It would all move offshore, production would move offshore in the process, and all of a sudden you've got leakages. So what you gain in California, or what you gain in the EU, you've got happening in the rest of the world, and the world doesn't end up any better off. As a matter of fact, it may be moving to developing countries where the technology is worse, and so you've got greater emissions. So in a sense, we've got to attack this as a global problem, and we've got to find a way of getting everybody on board. We can't let the developing countries totally out of this thing, particularly India and China. And the developing countries, I think by next year, are going to be producing over half the carbon and greenhouse gas emissions in the world. And they're growing very rapidly relative to the developed countries. So we've got some real big issues. And, this is a voluntary thing. Am I running out of time? Oh, I'm finished. Okay. A couple other things I want to talk about. The aggregate impacts, at least in some of the agricultural studies I've seen, are not going to be too great. It's the winners and losers by region and by local that are going to be big problems in the process. The U.S. is a big, diverse country. We'll have some areas that are going to lose, some areas that are going to come out better off in the process. And because of the technology that's been developed, like in the U.S., we've got enough adaptation opportunities that we can deal with some of this, at least in the short run, not in the long run. But when you go to other parts of the world, countries, particularly in Africa and so forth, are going to be really impoverished in this process. And they aren't big enough and don't have any place to go to gain from the shifts and movements in the process. Trade flows are going to change dramatically with this. Countries that are exporters may easily become importers, and countries may end up worse off. And so poverty and malnutrition are going to be a consequence of this in a big way. What are the added benefits and costs of action? Number one, there's no free lunch, so this is going to be costly. That's why I asked you the question I did at the beginning. It depends on how much we want to enforce this, but any way we look at it, we're looking at costly alternatives. And the tighter we set the cap, the higher we set the taxes, all of those are going to make things more costly. Secondly, there's no silver bullet, not even biofuels. And I do a lot of work in biofuels, so they're a long way from a silver bullet. But one of the problems I think we've got to be looking at is we've got to look at the whole set of technologies, and we've got to have a better assessment of what they're going to do with respect to improving or reducing greenhouse gas and carbon emissions. There are going to be some very disparate sectoral and aggregate economic impacts. I think the energy sector is going to face major disruptions. And the energy sector realizes that. That's why most of the big energy giants around the world in this country are investing big time now in moving into biofuels, because they see the writing on the wall. Or why General Motors is very concerned about global warming as being one of the biggest problems that they face. And what kinds of technologies should they be developing for the future in the process? I think also, though there may be some saviors here, we always kind of look at this as kind of a fixed relationship, but we can make a lot of substitutions. And we will make a lot of substitutions if the price incentives are right to make us move in that direction. And finally, I think it's going to generate some investment and economic growth opportunities. There's been a lot of work done by economists in trying to figure out what the costs were to the economy of environmental regulations in the 70s and 80s. And for the most part, I think the general conclusion is that they improved economic growth. Because we made new investment, we move forward. And if we can do an environmental program for greenhouse gases and carbon in such a way that it's not too disruptive, I think we can gain from it in the long haul as well. I don't see it as being necessarily a bad in that sense. There are going to be substantial environmental benefits, particularly in terms of the catastrophic consequences, as well as a lot of the efforts to avoid or adapt to changes in sea level and a range of other things. One of the problems, though, that we've got, there's a high degree of uncertainty on the added benefits and costs of taking action. But I think on the other side of that, there's a larger risk of not taking action. And that catastrophic risk on the other side is what really, I think, this is all about. Some of the short-term things we can adjust to quite quickly. The long-term things are not available to be played with in the future. The best policy options to achieve greenhouse targets, I will argue for market solutions over political solutions. And I'm going to come back to this in a minute. I think cap and trade and taxes are both good. And I think they'll both work. But politically, I don't think they're... I think cap and trade is more acceptable because people don't quite see what's going on as well as they do with another tax. And the polluters get the permits, so they don't feel like they're being cheated in the process. The other option, though, is do you want the government picking the winners and losers? And that's what we've really got right now. The government decides that biofuels are the answer, or wind energy is the answer. So we subsidize biofuels, wind energy, hydropower, on and on down the road. And in a sense, we subsidized nuclear for a long time with loose environmental regulations. So we had 3 Mile Island starting to melt down. If you want to put tight enough restrictions on, it's more costly, but you reduce the risk greatly in the process. So I think one of the things is the government has gotten to play such a role here that it makes it very difficult. Public versus private R&D. Again, should the government be picking the biofuels plants? I don't differ that they should be funding this research. I'm not sure they're the ones to pick the technologies. And so that's another source, I think, of what's going on. The government needs a lot of information, and we really need to be focusing on the greenhouse gas and carbon reductions, not on kind of what's the answer, what's the silver bullet. Let's see, the last. one of the things that I think reason I don't like the political solution is the devil's in the details of policy options. Congress legislates, they're lobbied very heavily, the administration implements. It doesn't always implement what the Congress legislates. And so the implementation, I worked in D.C. for USDA for about 11 years, and I saw a big disconnect there in the process. I think another thing we need to be doing is focusing on primary carbon sources. The primary sectors, the large carbon emitters. One of the problems we'll run into with a cap and trade, a tax system, or any other regulatory system is that any time we take it down, spread the burden around everybody, we have a lot more problems on enforcement. We have a lot more problems on making that kind of a system work. We can levy it on the fossil fuel companies and the carbon emissions. Everybody's going to pay for that. It's not just the fuel companies or the coal producers or whatever it is. Because basically that's going to mean everything's going to be higher priced in the marketplace. We're all going to pay. We're all going to have incentives to adjust and move down the road. I think what we're probably going to do, though, is focus on some hybrid combinations, more cap and trade, efficiency standards, which we're doing already back with the automobile, research incentives, and some way or other, we don't want to put it all on the producers or all on the consumers. We'd rather cut taxes for business, protect the consumers, if you listen to the campaigns anyway. And so I think we're probably going to end up with some problems in making this work well, even if we do it on a large global scale. My conclusions are, do we have the domestic and global political will to reduce greenhouse gas emissions sufficiently to avoid a catastrophe? And I'm not that optimistic. If so, the added benefits will be high, as will be the added costs will be high, but so will the added benefits of catastrophes avoided. If we use a hybrid approach, the added costs will be even higher due to some of the inefficiencies, and the greenhouse gas reductions will be lower. So we're not going to get the same bang for the bucks if we try to do it to keep everybody happy and let the political system work. Thank you. I'll answer questions later, I guess.
Thank you, Devin. Thank you for inviting me. I would like to talk to you about the technological perspective on reducing global warming. First of all, global warming is a reality, as Gene showed you, and the human impact is a very likely cause. And the question that I want to address is, what can we do to reduce the impact of humans on the environment? What kind of technological solutions are there? There's clearly no one silver bullet, but I just want to address some of the things that we can potentially do without winning 10 Nobel Prizes. First of all, let's remember that energy is not an end in itself. We don't use more energy because it's fun. The sole exception is weapons. Really, that's the only exception to the rule. Bigger the weapon, the better it is for whatever purpose it's meant to achieve. We use energy to achieve an end, transportation, heating, manufacturing, comfort, whatever. So the greatest immediate impact on global warming would be from reducing global warming would be from increasing the efficiency of energy utilization. And I want to show you some examples of what the better industries in the world are doing. And they're not necessarily American industries. And that, unfortunately, is true. How much energy does humanity use? This is consumption of energy in the United States in quadrillion BTUs, 10 to the 15 BTUs. We use approximately 100 Q of energy, and if you are in metric units, that's like 100,000 exajoules. This is equivalent to about 3.3 terawatts of power, continuous 24 hours a day, 365 days a year, or equivalent to about 3,300 nuclear power plants, 1,000 megawatt nuclear power plants going full blast. And this is energy consumption versus a year. And as you can see, the liquids, the oil amounts for the largest amount of energy consumption. The coal and natural gas are about the same. And nuclear and hydro and others are very small. And these are what the projections are. Of course, this projection is probably not going to be met because there isn't enough oil in the world at the present. There's not enough conventional oil in the world. There's lots of oil tied up in oil shale, and there's lots of oil in Athabasca tar sands and in Orinoco Basin, but that may be very difficult to get. So $100 a barrel is going to look like a cheap price 5 years from now. I'm serious. The world is using about 470 Qs, which is equal to 15.5 terawatts of continuous power. And this only measures marketed energy. It doesn't account for rural use. For example, wood. Wood is a major fuel for cooking all over the world, or cow dung. And so this is only marketed fuel. But that is by far the largest amount of fuel. And as you can see, we are somewhere here, and this is the projection as usual. And this is from Energy Information Administration. Now let me give you an example, power plant efficiency. The typical U.S. coal-fired power plant, old models, is maybe 33% efficient. Only 33% of the energy in coal ends up as electricity. If you do a little research, you find, you just type onto Google, power plant efficiency. Nothing more fancy than that. And then start looking at the papers. Thank God for Google. Prior to that, I had to go into the library and go through 25 journals. And now I can do it in 20 minutes. There's a plant, modern Hitachi plant, built in 2002, coal-based, 49.8%. Oil-based, 49.8%. Look at the difference in efficiency. They both give out the same amount of power, but one uses hell of a lot less energy. And the reduction in CO2 per unit of energy is 32% between these two. And there are advanced combined cycle plants, coal gasification. You gasify coal, use the gas in turbines, which are just jet engines, and use exhaust from the turbine to preheat the water that goes into the steam turbine. So there'll be a combined gas turbine and steam turbine. And all engineering projections show there's going to be 60% type efficiencies possible. And indeed, the Japanese are going all out for it. And the reduction in CO2, that versus that, would be a factor of 2 per kilowatt hour. We will not change our energy utilized. We'll simply change energy delivered. We'll simply change what we use to generate the energy. Now, why should we not be doing it? If Hitachi can do 49.8, what the hell is wrong with Americans? And this is the principle of just the way if Toyota can come out with a car which gives you 55 miles a gallon, why can't General Motors? Gas turbine burns the gas, and then the exhaust from the gas turbine will preheat the steam, and so you have a steam turbine and a gas turbine both generating power. And this concept has been around since I was a graduate student, which was 30 years ago. So here is a policy question. Is it so unreasonable to demand that every single new coal power plant be high efficiency? That can be done by mandate. If Japan can do it, why not the US and India and China? Actually, China is trying to do it. China is a political problem. The Chinese government wants the highest efficiency plants for a very good reason. They don't have as much coal as we do. Their coal reserves at the rate of growth are going to be gone in about 30 years. And so they are concerned. But Chinese government has very little control over what the provinces do. So long as the officials in the provinces bow to Beijing once a day and saying, you are great, they can do whatever they want to do. China and India are rapidly building new plants. China this year is building 88 gigawatts. That's more power than exists in the United Kingdom. Mostly coal-fired. Why not use the best technology? And they're trying, but there's significant resistance. And India is even worse. Indian power plants are much worse in terms of efficiency than either the Chinese or the American. Let me give you another example. Refineries. Oil refineries use a lot of energy. 7.5% of total U.S. energy consumption is by refineries. the largest single industry in terms of energy consumption. But not all refineries are equal in terms of something called the energy intensity index. The variations are by factors of 50%. You'll be surprised where the world's most efficient refinery is. It's not in Japan. It's not in the United States. It's not in Germany. It's not in Germany. It's not in Germany. It's not